Yes, please. Yes, thank you for the reminder, and please, yes, if I forget, which happens occasionally. All right, so we're talking about vectors here. We got the vector -4, -2, and that means a change in x of -4, change in y of -2. If I put that tail on the origin, then my tip actually ends up having the same coordinates as the components of my vector. Okay, so this is called in standard position. When you put the tail of a vector on the origin, it's called standard position. And again, when you do that, now the values of the components of the vector and the values of the coordinates are the same, but only when the vector is in standard position. Okay, so this one, so I'm going to put them both in standard position here. I got -4, -2, and then -1, -1, something like that. That's my u vector. And so you notice that you get this determines a unique parallelogram, right? So I could finish the parallelogram. Something like that. Erase here. All right, so I've got this, actually, let me draw that one. Okay, so you see that if you put two vectors tail to tail, you get a unique parallelogram. And so then what do you notice about this side of the parallelogram? So this side of the parallelogram is just vector v again. And then this side of the parallelogram is just vector u again. Okay, and so this parallelogram has diagonals. So there's one of them. There's the long diagonal. Let's just talk about the long diagonal. So what's the relationship of the long diagonal with vectors u and v? Do you see that if u is this vector here, and then v is on the tip of u, then you can see something important we learned from last class, that this diagonal as a vector is closely related to vectors u and v. Similarly, the shorter diagonal, the dotted line, shorter diagonal here, completes the triangle when u and v are tail to tail. Use this u and this v, tail to tail. This shorter diagonal could be a vector, and it completes the triangle of u and v, another concept from last class. So that's just a little hint on this. If you can find the vector for this long diagonal and the vector for the short diagonal, then all you need to do is find the magnitudes of those vectors, and you'll have the lengths of those diagonals. Okay, let's look at another example here. Any questions on that one?
Yeah, actually, I have like just a little question.
Sure.
So subtracting is tail to tail, and then addition is just tip to tail, right?
Right. So,
Okay, yeah. Okay,
yep,
thank you.
definitely.
Wait, could you repeat that again? The tail to tail is tail.
So yeah, so go back and review Friday's lecture when we talked about addition and subtraction. But yeah, if you've forgotten. But if I have this vector and then this vector, so addition means doing them both in succession. So where I left off in the first vector is where I want to start for the second vector. So now what's the one vector that does both of these in succession? Well, that's this one. So that's addition. So A first plus then B. So where you ended up at the end of A, you want to start with B. And then the one vector that does both those in succession is then A plus B. Subtraction is a longer discussion, so go back and review the video from Friday. Okay, so let's look at a different one here. This question. So we're on a ship here, and the ship is moving north. Okay, and it's moving north at 5 miles per hour. and then the child walks east at 2 miles per hour. So so we can come up with a vector for how the child is walking relative to the water. So the the ship is pushing the child 5 miles per hour to the north, and then pushing the child. Also, the child's walking 2 miles per hour to the east. So as a vector, we'll call it the walking vector, W. What's the x component? Well, it's 2, and the y component is 5. So in terms of the child walking relative to the water, the child has both these components. Has a x component of 2 and a y component of 5. So then the speed is the magnitude of that velocity vector. This is velocity because it's a vector. And the angle from the north, so 2 plus 5 is a vector like this. It's 2, 5. Then the angle from the north would be this angle right here. So you need trig. You're going to use a little bit of trig to get that angle measure from the north. Okay, any questions on that one? So those were the two that seem to have the lowest success. So I just want to talk about those briefly. Let's jump in. There's no questions. We'll jump into talking more about the basics of vectors. Okay, so the unit vectors. So we talked about the standard basis unit vectors last time, I and j. But just in general, a unit vector in general is any vector, can be any vector as long as it has a magnitude of 1. Okay, so any vector with a magnitude of 1, we call a unit vector. Okay, and so then we did have these special unit vectors called the standard basis vectors. Okay, and so then we said that I was 1, 0, and j was 0, 1. And so we're going to start talking about the coordinate space, which is three coordinates points make up space. And so in what we call it R3, in R3, then I will be the same. It'll be the x of an x unit vector in the x direction. So, but it'll have 2 more components. That's I. And then j will be 0, 1, 0. That's 1 unit in the y direction, and then 1 unit in the k direction. And so they're called standard basis because you can write any vector as a linear combination of the standard basis vectors. So any vector in R2 can be some scalar times I plus some scalar times j will give you, can represent any vector in R2, likewise in R3. Okay, so moving on here. So what are the effects of multiplying a vector by a scalar? Let's investigate that. So if u was -4, 2, say, then what would 3u represent? So what does multiplying a vector by a scalar, what does that mean for the new vector?
It just becomes 3 times as big.
Exactly. So it's going to maintain the direction. Direction stays the same, but it's going to scale it. That's why we call it a scalar, right? It's going to scale it or magnify it by 3. So -12, 6. So then each component gets scaled by 3. So the whole vector is 3 times as long in the same direction as the original vector. Okay, so what about, if I see here is 1, -7, 9, say. What about -0.5v?
It would result in a different vector with a different direction and magnitude.
Okay, so what about magnitude? The magnitude, first of all, would be?
0.5, -0.5, sorry. and then it would be positive 4.5.
But the magnitude, just the magnitude of the vector, will turn out to be half, because it's 0.5, half of the original, right? But then the negative does what?
Shifts the direction.
Now the vector is just in exactly the opposite direction. So when you have a negative scalar, you have two things happening. You get the reverse direction, opposite direction, but then also it's also going to scale it by whatever that factor is. So this is scaling it down by a factor of 2, right? So scaling down by a factor of 2, this scaled it up by a factor of 3. Okay, so what's the effect of multiplying a vector v by a scalar k? What does that do? So then k times v is it the same direction as v?
It is.
If k is positive,
Yes.
right? If k is
Yeah.
positive, you get the same direction as v. If k is negative, it's the opposite. So to generalize that, we could say it's parallel, right? It's parallel to v. And then the magnitude is scaled. Magnitude is v scaled k times. So that's generally what you get with scalar multiplication. Okay, so given that, what's a unit vector in the direction of 3i minus 5j? And what is 3i minus 5j? Remember, that's identical, exactly the same, mathematically equivalent, equal to 3, 5, right? Because we're scaling the I, this is scalar multiplication, right? We're scaling the I vector by 3, and we're going to scale j by negative 5 and add them together. So the same. So you can see that any vector can be a scalar multiple of some I, or some scalar multiple of I plus some scalar multiple of j, get you any vector in the plane. This is 3 times 1, 0, plus negative 5 times 0, 1. Well, that's 3, negative 5. Okay, so does this have a magnitude greater than or less than 1? Is it bigger than a unit vector or smaller? 3, negative 5. It has a magnitude of square root of 34, right?
Yes.
Square root of 9 plus, or square root of 9 plus 25. So magnitude of that, clearly bigger than 1. So this is longer than a unit vector. So we want to scale this thing down so that it has the same length as length 1. So how much do we scale it down by? How much do we shrink it by so it has length 1?
You
By the
multiply.
square root of 34, you divide it.
Yeah, right. So if it has a magnitude of square root of 34, and we want to scale it down to 1, then we're going to essentially divide by square root of 34, or scale it by 1 over radical 34. So now 3 over radical 34 minus 5 over radical 34 is going to be what? That's going to be have the same direction as 3, negative 5. And now it's going to have unit length because we've scaled down a vector of length radical 34 by radical 34. Taking 1 radical 34th of it, right? And so then that will have magnitude of 1 now. So that's a unit vector. That's a unit vector right there. Makes sense. Okay, how about this next one then? All right, so now this is kind of takes us to the next level here. Find a vector that has magnitude 8 in the opposite direction of negative 2, negative 7. So what about 8 times -2, -7? Does that do it?
No.
What about the magnitude of this? Is the magnitude of this bigger or smaller than 8?
Bigger.
Bigger.
Bigger. The original vector has a magnitude of square root of 53, right? Square root of 4 plus 49. Okay, and so if I multiply that vector by 8, well, now the magnitude of this is going to be 8 radical 53. Way bigger than 8, right? So what if I want a vector with magnitude 8? The easiest way to do that is to have a unit vector that I multiply by 8, right? If I have a unit vector that I multiply by 8, well, I just forced the new magnitude to be 8. Okay, so we know how to do that, right? So we know how to find a unit vector for this vector, and then by multiplying that by 8, then we just scaled it back up to 8. So we want to scale it down to 1 and scale it back to 8. So how do we scale this to a unit vector, to 1?
Divide by the magnitude.
Yeah, we're going to take 1 square root of 53rd of it. Now we just found a unit vector. So this is the unit vector. Now we want its magnitude to be 8 and face the opposite direction. So what do I do now with this?
Multiply by -8.
So multiplying this by -8 will give us magnitude 8 and flip the direction. So I'll have -8. We get the fit here. So what will that be? Positive 16 over radical 53 and 56. Can you still see me writing over here?
No, Professor, the writing is hiding.
What happened?
I cannot see the writing is all the way down.
You can't see anything I'm writing because it's at the bottom, or you can't see this because it's on the right?
It's in the bottom, so it's way down the bottom. So.
It's not all covered up, just part of it.
Okay.
We can see the numerators.
If you make it full screen, you can see it all.
I thought I was full screen. All right, so I'll just write it again up here. So this is our unit vector. And I'm going to multiply that by -8. And so final result, positive 16 over radical 53, positive 56 over radical 53. So we just forced, this vector has, what, magnitude 8, because it's 8 times a unit vector, right? 8 times a unit vector gives magnitude 8. And then opposite direction, it has both positive components. Questions on that example? So that's an important skill to have. And rather than just memorizing a procedure here, it should make sense, right? So if I want a vector with magnitude 8, well, I want to scale a unit vector by 8, right? So I got to find the unit vector. And the unit vector will be a scaled version of the given vector, scaled by 1 over its magnitude. Okay, any questions on that one? All right, let's look at another application example here. So here's an example, force example. So I have two forces that are attached to the origin and pulling with a force of 4 kilonewtons in this direction. That's vector A. Another force vector pulling with 2 kilonewtons in this direction. That's vector B. And I want to find the component versions of these two vectors and also the resultant force at the origin. Okay? in both component form and polar form, like we talked about. Okay, so let's do the components of A and B first. So these are given in polar form, right? They're given in magnitude, direction form. Okay, and we want to get the components. So what's that going to entail here? So say for A, you know, all vectors can be broken up into a horizontal component and a vertical component, such that that horizontal plus the vertical component is equal to the vector itself. So how am I going to get this horizontal component?
Multiply 4 by the cosine of 40 degrees.
Yeah, so this should look very familiar as a trig situation here. We got the angle here, we've got the hypotenuse, and then our components are the two legs of a right triangle. So 4 cosine 40 and 4 sine 40. Okay, how about B? So is B 2 cosine 10? 2 sine 10? Is that right?
No,
Someone said no.
it's not in the first quadrant.
Okay.
I think it should be 2 cosine of 170 degrees.
Right. So remember, cosine and sine are based on, your angles are based on counterclockwise rotation from the positive x-axis. So this is not your standard, this is not the angle measure that sine and cosine are expecting. If you give sine and cosine of 10, it's gonna think it's this. That's 10 degrees, right?
Would it be a negative as well because it's in the
like negative quadrant?
Okay, so there's
Negative.
two ways. Yes, right. So there's two ways to resolve this. So so we can use 10 degrees if we do what? First of all, so this is not right. So we can use 10 degrees if we do what?
make it negative?
Yeah, just make what about the y component?
Y component can stay the same.
Yeah. Yeah, so this is still, even though we're here in the sine of 10, the sine of 10 is actually the same as the sine of this direction because they're both positive. Sine is the y coordinate. But with the x component, if we do cosine of 10, then we have to take the opposite because x is negative here in the second quadrant where x is positive here in the first. So that's one way to do it. And someone else had said we could do this. We could just use the correct trig angle, which would be 170. So either of these are going to get us the right B vector. Either take the opposite of x because we're in the second quadrant and use that 10, or just use the angle, and when you use 170, it'll take care of all your positives and negatives in all four quadrants, right, correctly, if you've got the right angle from the x-axis. Okay, so next question is, if I want to know, let's talk about the situation here. So we've modeled this with these vectors that are two-dimensional vectors, right? So it's kind of like, these are kind of like displacement vectors. In this situation, does that point, so we're pulling in, say, a bolt, okay, in the wall. So this is a bolt, okay? Does this point on the wall, is that meaningful, relevant? Here at the tip of A? Is my force also pushing at this point on the wall?
No.
No. So you should see that points away from the origin are totally irrelevant in this scenario. So this point at the end of vector B, it has no bearing and no relevance in the context. And same with this here. So we're kind of using like these displacement vectors to not model displacement at all, but really to model the force right there at that point only. So all the focus in this analysis is right around right at the origin, what the force on the origin is, even though we're drawing stuff out here, right? We're drawing stuff out here away from the origin to represent, to be representative of what's happening there. So these locations, what I'm saying is these locations out here away from the origin, totally irrelevant. The whole diagram is about what's happening right there. Okay, so we want the resultant force at the point. The total resultant force. So would that be adding or some kind of subtraction?
It'd just
I
be
want
adding.
Adding.
Someone said adding. What about the fact that these vectors have been shown tail to tail?
Tail to tail, yeah, subtraction.
That just means that's where
Doesn't
it's
matter.
the force is being applied from, or on
Yeah.
that point.
Right. So this was the diagram given to us, right? So just because the diagram was given to us with the vectors tail to tail doesn't indicate addition or subtraction. It's when you have an addition or subtraction, say a subtraction problem, and you want to model it, that you would set the vectors tail to tail. It's kind of like the reverse, okay? But just because they're tail to tail doesn't necessarily mean subtraction. In fact, in this case, we do want addition because we just want the combined total, the total contribution, the combined effect of both forces. So we want addition. And so if we want, we can go tail to tail, or sorry, tip to tail for addition. So I'm going to take B. I could put B right there like that. And I'm doing A plus B. And so that shows us that the resultant force at the origin, if you just had one vector pulling on the origin, it would be like this vector here. Okay, so based on this rough sketch, we're expecting what? Some angle between 40 and 90 degrees, and maybe some total magnitude less than the magnitude of A, right? So that would just be kind of a rough way to check our final answer. So to do A plus B, we've got component form. The beauty of component form makes computations easy. Apples to apples, oranges to oranges. So we can just add them up. Add X components, add Y components, rather than write that all out. And I just remember that the answer is about 1.09 kilonewtons in the X direction and 2.92. Again, where's that coming from? The X component of A plus the X component of B, and then the Y component of A plus the Y component of B. All right, and so that's component form. What about polar form? So polar form is where we have magnitude and direction. So magnitude is sum of the squares, square root. That will be the amount of force in kilonewtons. That's the combined effect of A and B together. And then what about angle? So if this is 1.09, oh, I'm going to off the screen again. So how about that? That's 1.09, and this is 2.92. Then we're asking about this angle. How would we find that angle?
Tangent of 2.92 over 1.09.
Okay, so actually I want the arc tangent, right? So it's the tangent of the angle that gives that ratio that you said. So we want the arc tangent of 2.92 over 1.09. And if you do that, you should get some angle around 60, 70 degrees, something like that. And this magnitude will be something less than 4, something between 2 and 4. Greater than 2, but less than 4. Okay, questions on this problem? Okay, so let's talk about I mentioned earlier, the R3 coordinate system. So modeling things in space. So now 3 coordinates to model locations in space. So here's what that looks like. So here is trying to render what, three-dimensional space on a two-dimensional screen, right? And so, yeah, it's made to trick your eyes into thinking that this axis right here is coming straight out at you, right? It's not pointing down and to the left in your relative to you. It's pointing straight out of your screen, right at your heart, right? It's like a spear. It's going to go right through your heart if it came out, okay? So we've got our coordinates are, this is R3. Coordinates are X, Y, and Z. You remember in R2, of course, that coordinates are X and Y. And so natural to think that here's X, here's Y, just like your XY plane that you've been living in for your whole math career, and then here's Z. Okay, but that's not what it is. That's not what it is. Intuition is not served here. Instead, this is the x-axis, and this is the y-axis, and this is the z-axis. Okay, so let me show you, but, the xy plane in R3 is the same xy plane in R2. You have to have a good spatial concept of that when you look at the xy plane in R3, it has all the same features, characteristics, and use and application as the xy plane in R2. So how does that work? So I got my daughter's easel. You see my daughter's easel here? My video's on, right?
Yeah.
Okay, so can you see my daughter's easel? My daughter, the artist. Okay, so so here I'm showing the xy plane. Can you guys see that?
Yes. Could you bring it a little bit closer, the camera?
How about that?
Yeah, it's much better.
All right, so there's the xy plane. So what we're going to do with the xy plane, this is the way this is how you've lived, and you're so conditioned to this, right? X to the right, Y is up, okay? And so what I'm going to do is I'm going to take the xy plane, and I'm going to give it a turn like this, and then I'm going to turn it down like this. And now that's the way the xy plane is oriented in R3, in three-dimensional space. One more time. Here's your conventional view. I'm going to take that same plane that you've been living in your whole life. I'm going to pick it up and rotate it this way, and then turn it down like this. So now where's X? X is coming right out at you, and Y is to the right. Does it make sense? One more time. I'm going to take it and turn it and rotate it down like this. So now I'm looking at the same XY plane that we've always used, but now my X is out coming at you and Y is now to the right. Okay. So because of that, we've got the what? We've got the four octants. Sorry, the four quadrants, right? So where are the four quadrants then in R2, in R3? Okay, so here's our XY plane that I just showed you. So where is the first quadrant? It's here. First quadrant's here. Second quadrant's here. So this is consistent. It's the exact same numbering of quadrants that you've always used. Because quadrant 1 is where X and Y are both positive, upper right. So this is upper right, in fact. Upper left, lower right, okay? So then, with these axes, we have three coordinate planes. Not just one anymore, there's three. The XY plane is the same one we've always done, but now it's horizontal. It's the same one you've always used. Everything's the same about it. There's the YZ plane. That's the vertical plane of the screen or your piece of paper or whatever you're looking at, the page on the book. It's YZ is the plane of your screen or or the plane of the page if you're on paper. Okay, the XZ plane is another vertical plane. So I'll draw the X. I'll kind of draw that. Here's the XZ plane. See that? That's another vertical plane. This plane is perpendicular to your screen, and if it came out at you, if it was like a giant like knife, it would slice you in half vertically, right? It would slice you right down the nose, down the heart. So there's two vertical planes, YZ and XZ. YZ is the plane of the screen. XZ is the plane that comes straight out and cuts you in half as a person looking at the screen. And then the XY plane is the horizontal plane, and it's the same XY plane, just like turned and laid down the way I showed you. Okay, so the three coordinate planes then break up space into 8 octants. Okay, you have 8 octants that are broken up by these planes. So it's something like this. So that's my attempt to draw all 3. It's not too bad. And so you've got 8 octants. And so let me show you. So the octants are numbered. They're numbered just like the in the same kind of pattern as the quadrants. Okay, so let's look at that. Okay, so here, this box is in the, so since the quadrants were, since the quadrants were what? 1, 2, 3, 4. Those are my quadrants in the XY plane. So we're likewise going to go around, and the first 4 octants are the same for above the XY plane. So you see this box is above the XY plane. It's in the first octant. Okay, and so then that box is in the second octant. Third octant. Fourth octant. Back to the first. Okay, and so that's 1, 2, 3, 4, and then the 5, 6, 7, and 8 are the same pattern again going around, but all below the XY plane. So here's the 5th octant, 6th, 7th is back to the left and below, and then 8th octant is below, to the left, and in front. So that's the 8th octant. Okay, so does that make sense? So you got the 3 axes, you got X, Y, and Z. You got the 3 coordinate planes, the XY plane, the YZ plane, the XZ plane. And then you have 8 octants that are those 3 coordinate planes divide up space into 8 octants. So up above the XY plane, 1, 2, 3, 4. Down below, 1, 2, 3, 4. Okay, so plotting points. Now you have 3 coordinates. So this is the point right here. 3, 5, 2. So point P, say, is 3, 5, 2. That means your x coordinate is 2. Or 3, sorry. So x-axis is first now. So the first thing you do is you come out at you if it's positive x. So 1, 2, 3. And then y is next to the right. 1, 2, 3, 4, 5. And then up 2. So that's the point 3, 5, 2. Okay, so that's point P. So how far, first question, how far is point P from the YZ plane? So distance from P to YZ plane. Well, you should be looking at this right here. Right there, that right there is showing the distance to the YZ plane. What is that?
That's just the x value, so it's 3.
Yeah, so it's 3, right? It's 3 away from the YZ plane. So point P is 3 units in front of your screen. That's the way you think of it. Point P is 3 units in front of your screen because it has an x coordinate of 3. All right, what about the distance from P to the y-axis?
5.
Okay, is it 5 to the y-axis?
3.
Is it 3? It's either actually neither of those.
Wouldn't it be the length of like kind of the vector coming from the y-axis with values of the x and z?
Exactly. So the
Components?
distance, if you were to go travel along the line to the y-axis, it'd be that would be what would characterize your displacement from P to the y-axis would be along there. So we can make a vector.
The square root of 34?
Square root of 13.
So this point on the y-axis is the important point to answer this question. I call it Q. To answer this question, how far is it from P to the y-axis? So what are the coordinates of point Q?
0, 5, 0.
Good, 0, 5, 0. It's on the y-axis, so it has x and z components of 0. So 0, 5, 0. And so we can make the vector PQ. And vector PQ would be, sorry, I drew QP, so that's what I meant, QP. So QP would be, so we can, to find out, we do the components, final minus initial, right? Components of P minus components of Q, that will give me the vector QP. So what is that?
3, 0, 2.
3, 0, 2. So that's that vector right there, 3, 0, 2. Remember, vectors are mobile. I could draw that here. Back up in the second octant. Down here in the 8th octant, I could draw that, 3, 0, 2. Vectors are mobile. Okay, and my original question was, how far is it from P to the y-axis? Well, that's the same now as going to be as the magnitude of QP, square root of 13.
How did we get the 2?
This 2?
Yes.
Yeah, so from Q to P, we're going to, so from Q to P means we're going to do final minus initial for each component. So 3 minus 0, 5 minus 0, 5 minus 5, sorry, 2 minus 0. So the change in x is 3, the change in y is 0, and then the change in z is 2.
Oh, okay. Thank you so much.
Sure. Okay. Man, I went as fast as I could, and I still didn't make it. I'm gonna finish this up as best I can here. Questions so far. So now, what are the coordinates of this point? I'm gonna call this point C. What are the coordinates of that point C right there?
3, 5, 0.
He wants 3, 5, 0. Agree with that?
Yeah.
Yep. Okay, so I want every point a distance of 2 from C. So how can I represent every point? If every point, it's variable, it's moving around, so I can just say Here's one of them. So here's one of those points that's 2 away from 350. I'm going to represent all of them by x, y, z.
Or a sphere.
So let's do it. So now I want the vector from C to my arbitrary point. What vector is that? I'll call it, I'm going to call it vector R. What vector is R from that point to any point x, y, z? Vector R would be? Final minus initial, right?
Minus y, z minus 0, or 0 minus z.
So it'd be x minus 3, y minus 5, z minus 0. That would be the vector from C to every point in space, x, y, z. And now I want to force that to have that magnitude to have that vector to have a magnitude of 2. So I'm going to take the magnitude of this vector, x component squared plus y component squared. I don't need that right now. This was not what I needed right now. Actually worked. Okay. So there's the magnitude of that vector, and I want to force it to be magnitude of 2. If I get rid of the square root by squaring both sides, it's the same equation. And so this equation then represents all points 2 away from 350. And what are all points the same distance away from a point in space?
Sphere.
Someone said earlier, a sphere. And so this sphere has center. That's why I called it C, 350, and radius 2. Okay, so we're a little bit over. Thank you for your patience. So with the quiz is open until midnight tonight. You can take it anytime, don't forget. Okay, so take the quiz. You can take it now, you can take it this afternoon, you can take it this evening. Okay, but it closes at midnight tonight. So make sure you take that quiz on today's stuff. WebWorks due also tonight at midnight. And then
This is the R3 basics, yeah.
the quiz is called, yes, sorry. The quiz is called R3 Basics, and it should be open now. Yep, quiz is R3 Basics.
And the homework is just the R3 and vectors basics, correct?
So far, there's just one WebWork open. I may open a second WebWork this afternoon. That won't be due tonight. It'll be due later, but if you want to get started on it.
Okay.
I'll stick around right now for any questions. I'll stick around and answer your questions. Otherwise, have a great day, and stay up to date on Canvas. Has everything you need for due dates, and I'll see you on Wednesday.
Thank you.
You're very welcome.
Thank you, Professor.
Hey, Professor, how does spheres factor into this?
Well, based on the problem that I introduced a situation. In that situation, the solution to that situation ended up being a sphere. The situation was all points the same distance away from this point C.
Oh, okay.
That was the first thing. That was what we were looking for.
Right.
So I called all those points X, Y, Z, and we forced the distance from X, Y, Z to 350 to be 2.
Okay.
By making a vector and taking the magnitude of that vector and forcing it to be 2. But then if you think about it, it's like, what are all points the same distance away from a point? Do you see that that's a sphere?
Right.
Yeah, so then this turns out to be what we found by doing the magnitude of the vector being 2. We derive the equation of the sphere.
Okay.
Is that better?
Yeah, that's much better. Thank you.
Okay, cool.
Thank you.
You're welcome.
Professor Ashbrook,
Yeah.
I have a question about the homework, if that's
Sure.
okay. So, you did go over this problem, but what I've been confused about is, despite following those steps, I still seem to be getting the wrong answer, at least according to WebWork.
Okay.
It's the one with the boat and the child.
Yeah, sure. Okay.
So, for me, the boat is going 20 miles per hour north,
Okay.
and the child is going 2 miles per hour to the east.
Okay.
So, I got the correct speed at which the child is going, 20.1 miles per hour.
Okay.
But what I keep getting wrong is the angle of the direction from the north.
Are you entering it as radians or degrees?
Radians.
Is that what it says?
Yep.
So it may be. So I heard you say that the magnitude was like 20 point something. So
8.1.
a nice thing about WebWork is that you can enter in expressions like instead of getting to a final answer and on your calculator and getting a decimal approximation, you can enter in. So like for that magnitude question, the safest way to enter that would be to do square root of 4 plus 400, or if you want to do 404 or whatever, and you can actually enter in that. And then you never have to worry about how many decimal places because you're putting an exact value in.
Oh, okay, I see.
So I think the same thing applies to the angle. So rather than punching some arc trig function in your calculator and putting a decimal approximation in, go ahead and put an exact value in using a trig function.
So would it be, would I write either inverse tan or arctan? Does it matter which one I use?
Do they still have the equation button to the right of the entry box?
Yes.
So if you do that, you can like scroll through all the options of like functions and you can find arctangent. It might be spelling it all the way out, ARCTAN. That's what I guess it is.
That seems to work. So
yeah.
then
So then do arctan, then put in the ratio, and don't do any punching on your calculator. Let WebWork be your calculator.
So then it would be arctan 2/20.
I believe. Yep. And then you never have to worry about decimal places.
All right, thank you. That was my last attempt. I was worried.
Oh, okay. You got it?
Yeah, thank you.
Very good. Okay, good. Who else? Anybody else have a question right now?
I have a
question.
Oh, go ahead.
Okay, I just tried that, and I put in arct. Oh, I think I spelled it wrong. I think I put ARCT. Dang it! So I got it wrong.
Oh,
I
sorry.
suck.
Do you have any more attempts left?
No.
Oh. So that's the kind of, a spelling error. That's kind of the reason for the multiple attempts, like typos, right? So we want to get all those out of the way with the earlier attempts.
What section of the book could I find what we're learning right now?
It's in the syllabus.
Oh, okay.
But you're looking just, it wouldn't be hard to find. I don't know off the top of my head, but you're just looking for, the introduction to vectors and introduction to the R3 coordinate system.
Yeah, both. Yeah, I'm just trying to.
I think it's looking in the chapter, the table of contents.
Yeah, that's where I'm looking right now.
Yeah, it should be pretty obvious in the table of contents. But it's also on the syllabus.
Okay, thank you.
Okay, you're welcome.
I have a question about find the unit vector in direction opposite to v equals 4, -4.
Mm-hmm.
And I punched in the answer that is -4/4, but I think that's wrong, and I don't know.
Yeah. Why is it wrong? That's definitely wrong. Why is that wrong? What is it asking for?
Find the unit vector in the opposite direction to
What kind of vector?
Unit vector.
Unit vector. What's a unit vector?
It has a magnitude greater than 1.
Mm-mm. What does, you know what unit means? You know what the word unit means?
No.
It means 1.
Okay.
So a unit vector has a magnitude of 1.
I will try that out. Thank you.
Okay, sure. No problem. Who's next?
So, real quick with the octants,
yeah.
I'm just gonna, could I say them all just to make sure I have them in the right order?
Yeah, sure.
Okay, so starting with the normal ones from above the XY plane, okay, you have going counterclockwise, first, second, third, fourth, and then below that, then you have fifth, sixth, seventh, eighth in the same order, basically.
So it follows the exact same pattern as your quadrants.
Okay.
First, second, third, fourth quadrant. So you're always starting in positive territory and going around counterclockwise. So for the 8 octants, you go around for the first 4 above the XY plane, and then you go around the bottom 4 below the XY plane.
Okay, cool. And then how did we derive the equation for R there? How did we figure that one out?
This vector R?
Yeah, vector R.
Well, so the starting point was always 3, 5, 0.
Okay.
And then I was saying every point that's 2 away from that C. So if it's many points, then I chose variables to represent like all possible points. Do you see that?
Yes.
So the coordinates of C is 3, 5, 0 at the tail, and the coordinates of the tip were just X, Y, Z.
I see.
So how do you find if you got the 2 coordinates of your tip and your tail, how do you find the vector?
Sorry. You take the 2 points and then you do the final minus the initial.
Right.
Okay.
You see
That makes sense.
So then
Yes.
that's so X, Y, Z is always at the tip. It's just many points, right? So it's just like arbitrary.
Okay.
So that's where I got final minus initial, final minus initial, final minus initial.
All right, that makes sense.
Yeah.
And we just set it to 2 to get the magnitude, for any point.
No, I set the vector's magnitude
Right.
to 2 because
Okay.
that was the scenario I laid out. I said I'm interested in all points a distance of 2 away from C. So I want all those vectors R to have a magnitude of 2.
All right, that makes sense.
Yeah.
Thank you.
Sure.
Professor?
Yeah.
I was wondering, how do we do on the homework problem 5? It's the one with the dragon, the 9 waves going northwest with the wind coming at 59 miles per hour from the west. I know is it supposed to be a trig setup?
Yeah. Actually, it does. Let's talk about that. But before we do, before I erase this, I just want to see if anyone else has a question on kind of where we left off at the end of class before I erase what I wrote. Does anybody have a question about these vectors or the sphere or anything? Okay. So I'll clear that out. All right. So tell me what was your problem again?
The 9 wing waves want to fly to Rivendell, which is directly north, and the wind is coming from the west at 59 miles per hour. In order to travel in a straight line, the waves decide to head northwest. At what speed should they fly?
Yeah, that's a good problem. Okay. So this is our unknown. So this is like, this is our velocity, right?
Okay.
So these are the 3 vectors in the problem. It's the way the wind's blowing and the way that we're like, is it flying? Is it in a plane?
Yes.
the way that we're flying, and then the resultant movement of the plane, right?
Okay.
So if this is the wind, that's V, and then I'll say just call this M for movement. So what's going to be the relationship between W, V, and M? How will W, V, and M be related? You know?
M should push V to M, so V should increase as it goes to the left, while W stays.
But I'm looking
stable.
for a mathematical relationship between these three vectors.
You would W minus V.
So what's happening? The plane, the engine of the plane is trying to do this.
Yes.
And the wind is doing this.
Okay.
And then as a result of those two things together, the plane is doing this.
Okay.
So what equation would that be?
W minus V. So
No.
W.
So the plane is doing this, the wind is doing this, and then the result of those two taken together results in the plane moving like this.
Okay, so WV equals M.
W
minus.
No, it's gonna be plus, right? Plus.
Oh. Okay.
Does that make sense?
Yes.
The wind is blowing the plane this way. The engine is blowing the plane this way. Okay. And the resultant motion of the plane is this way.
Okay.
So you're going to add V and W to get M.
Okay.
Is that okay?
All right. Yes.
So what is W? We can just write it down. What is the vector W in component form?
59.
Okay, that's just a number. That's just a scalar. It's a vector, right?
Oh.
So what's its vector?
Yes. The vector would be 59 and 0.
Right. Now what about V? So we don't know what the values are, but we do know something here. We do know something that it's what? Directly northwest.
So it would be negative for the X and positive for the Y.
That's good. That's a good start. Okay, so negative for the X, positive for the Y. And so then if it's directly northwest, what can you say? How can you compare the X and the Y? How do they compare? If it's directly northwest, what about those two components? So like this is like 45 degrees, right?
Correct.
So if it's a 45-degree angle, what about these two components? What could you say?
They have to be pressure marks would have to be the same magnitude.
Exactly. Right?
Yes.
But you know that you want this to be negative and this to be positive, so how can we model that?
Negative X, positive X, or different A. Yeah.
No, X is great.
Oh, cool.
Let's do X. That's fine. Perfectly fine. It's just a little weird because then X is a little weird because now your Y component is X.
True.
So that's why I think maybe A is better.
Yes, that's right.
Okay. And then what about the resulting M? What can you say about that?
M would be, since it's only odd, it would be 0, 0.
0? That means the plane is standing still in the air.
Oh, so it would be 0, and it just says directly north, so that would be infinity?
No,
that doesn't feel right.
Then you'd be flying at the speed of light.
No.
So just take a clue from what we did here. What did we do? We didn't know what the value was, so what did we do?
We made the values equal.
Well, no, that was because it was a 45-degree angle. But what did we do because we didn't know the values?
We applied trigonometry laws.
No, we just chose a variable.
Oh, okay. So B.
Yeah. So it's gonna be heading in the north direction. We just don't know how fast. So that means 0 x component and b y component.
Correct.
So now I think the problem just got very easy.
Yes.
So how do you add? What do you do to add vectors?
Just add them straight across.
Add like components, right?
Mm-hmm.
We add x's.
It'll be 59 minus a.
So I think you can finish it from there.
Yep. Thank you.
Okay, you're welcome.